Okay, so we defined what was the pointing vector, and now we also notice that pointing vector, it was a function which is like E cross H. Okay. We also notice that, or remind ourselves that E dot J, this is ohmic loss or dissipation. So this is ohmic loss, or energy dissipation, or energy loss in the form of heat. And let's see, for example, let's try to see a case like this. So assume that we have a capacitor, and this capacitor, it looks like, so we have a current that is flowing in a capacitor. In principle, often if you connect an alternating current power source, okay, so this is a VC or VAC, so the voltage, input voltage, is going to look like this. So this is the voltage, this is the time, and it's going to be a sinusoidal behavior, okay? We expect it to be a sinusoidal behavior because when we talk about a capacitor for a DC current, poate because space void my battery, I have got short circuit, so you block it. Okay, so it is a short circuit for DC current. For this reason, we can apply only an alternating current, which is going to look like this. This can be a capacitor here. You can have also a resistor, or a resistor can take it out completely. But here, so this part of the circuit shown here, we blow it up and we we show in this case. So here we have the current I, and this current I, this causes, so here, because the current that flows, you remember, we can have here an electric field E. Okay, so this electric field E is because we have a charge here. This can be a charge plus, a charge minus. Okay, the charge, it will oscillate, and because of this we have this electric field E, and this is denoted as, let's assume for a moment that we use cylindrical coordinate system. The cylindrical coordinate system, we have the Z, so this is the Z. We have the R, which is the distance from the central axis. Okay, so let's assume that this is the center, and this is the AR, and this is the AZ. So the electric field is pointing along the AZ. And let's see what other components we can extract here. And we know that for these kind of systems, whenever we have an electric field which is changing as a function of time, so this E, let's also denote this E is E of t. And we know that whenever electric field is changing as a function of time, we generate a magnetic field. And the same thing also happens. If a magnetic field is changing as a function of time, this induces or it produces a new electric field. So we get here H is equal to H of t. But how is the H related to E? We have the Maxwell's equation. So they are coupled together, okay? And the coupling of the E and H, they are shown by the Maxwell's equation, and we can write this expression. The line integral of the magnetic field intensity and the closed line integral, this is equal to the rate of change of the D. So this is the displacement vector, epsilon permittivity times the electric field, d over dt, so this is the rate of change, times ds. So how do you understand this? We can draw a closed contour like this, okay, inside this capacitor. And we expect to have a magnetic field H intensity, which can circulate like this. And this line integral, this is going to be equal to the rate of change of E times ds. ds is this surface area here, okay? So this is how we get, so we apply the Stokes theorem to one of the Maxwell's equation, and the Stokes theorem is applied to the current of H. So once you apply this to the current of H, this is what we get. And here we get something in the order of this, like H times 2 pi r, because the line integral, this is the perimeter of the outer contour of the circle is 2 pi r, this is going to be equal to permittivity times pi r squared times the derivative of E with respect to t, dE over dt. Okay, so this is what we obtain. Now, and also, so we learned actually what is the magnitude of H. But H, so E itself, E, it's E times AZ, okay? H is, as a vector, is the amplitude of H times A phi, okay? So when we say A phi, this is circulating or is moving in the direction of where phi is increasing. We know what A phi is, right? So it's going to be, at any point here on the circle, it's going to be tangent to this circle, here and here. Then the question is, what is the Poynting vector? So what is the energy flow inside this capacitor? If you have E and H, what should we get? We get E cross H. What is E cross H? This is equal to, let's leave aside for a moment the magnitudes. Let's just look at AZ cross A phi. So the way to do this, we often do it like this. So we have the coordinate system is R, phi, Z, right? And we know that AR, A phi, and AZ, we put them like in a cyclic permutation. So in this case, we know that AR cross A phi is equal to AZ, right? So we say that AR cross A phi, this is equal to AZ. Okay, now here we have AZ cross A phi. AZ cross A phi, this is moving counterclockwise, so this is moving backwards. So here we get AZ cross A phi, this is equal to minus AR. Okay, and again, if we come backwards, like counterclockwise, AR dot AZ, this is we're done. This is all we need actually, but as a reminder, we have AR cross AZ, this is equal to minus A phi. And if we go clockwise, like here, for example, we get AZ cross AR, AZ cross AR, this is equal to plus A phi, okay? But all we need is this, which means that this is going to be equal to, of course, we can multiply also with the magnitudes of the intensity, electric field intensity, and the magnetic field intensity. And here we get the minus A phi. No, sorry, minus AR. So what does this mean? This means that the energy flow, it flows into the center of the capacitor. So you have a capacitor which is composed of two circular plates. So you have two discs, and two discs, they have charges here, electric field and magnetic field. And now you have the flow, which is it's like an inflow. So if you look from the side, so this is the capacitor. Now the current is flowing into the central axis. Let's call it this way. Okay. So this is how the energy is flowing. So this is how we can visualize it. Now, a similar visualization can be done also for a wire. So let me erase this one for a second. So for a moment, actually, everything will be more or less the same. So we have a capacitor, which we denoted like this. There was an electric field that flows like this. Now, for a wire, it's going to be almost the same problem. Okay, so we can write this very fast without spending too much time. So let's imagine we have a wire which has a current I. It has a radius R. If it is a current I radius R, we can immediately extract a J, which is equal to I over pi R squared, right? Because I is a current measured in amperes, A and B. R is the radius. So if this is the case, we know that the wire, it has also a conductivity. So we have conductivity sigma here is different from 0. And we can also report that we can find that the electric field that flows is equal to J over sigma. And this is equal to I over pi r squared over sigma. And this is E AZ. Okay, so in a wire, we have an effective electric field. And why is this? Because we know that in conductive materials, the J is sigma E. Okay, so external electric field, because that's how we apply the current in a circuit. So we connect a wire with a potential difference. So we create the electric field over there. If it is conductive, we multiply the electric field with it, that's what we get. So this is the J, and then we can also find similarly, so the H is going to be the same thing. So if we have an electric field flowing here like E, like this, we're going to get a magnetic field which is going to circulate exactly the same way that like a capacitor. So here we can simply state that this is going to be a magnetic field intensity, which is I over 2 pi r A phi. Okay. So with these numerical values, actually we can do more correct. When I say correct, let's follow here. Let's take care also of the magnitudes of the specific fields. But so far, we are just seeing these specific values, and for H and E, and let's see let's start here. The Poynting vector S. This is E cross H, and the E, this all together, this is equal to AZ cross A phi. This is just shows the direction of the vectors times electric field E I 2 pi r, and this is equal to, the direction is minus AR. Okay, so this is the result of the cross product of these two unit vectors. And then for E, let's see for a moment what was E. Well, E was equal to, so we can extract E from here. So E is the current divided by pi r squared sigma. This is current I divided by pi r squared sigma. Then we multiply here with I again. Current I over 2 pi r. So let's not forget I over 2 pi r. This was the magnitude of the H. Okay. So then here we continue again. We say minus AR times I squared over. So here we get a few terms, which is going to be 2 sigma pi squared r cubed. So, and then here we also let's not forget what was the unit of this quantity. What was the unit of E cross H? Okay, so here we are. This is watt per meter square. And the direction is, so we know, let's try to visualize this one. We have a wire, and this is the wire. And the electric field, we assume that it was going up. So the electric field is shown like this. The magnetic field is showing like this. So it's circulating continuously so it's tangent here, tangent here, tangent here. And then, as a result, we observe that we have an energy flow, which is into the center. When you see it is into the center, so it's pointing like this, or including like this, like this, like this, and so on. So you have the energy going that way. And now the question is, we can also notice that this is shown by this AR, minus AR, so it's pointing in this direction. Now, if we want to integrate this one over a surface area, what will be the area over which we are going to integrate? So my question is this: if we're going to do this the area, which one will be the area? Often we know that the dot product between two vector quantities, it goes like this. So if the S is pointing into the object, to the center of the cylinder, what should the direction of the area be? It should be a vector which is perpendicular to the surface area, because we know in electromagnetic field theory, it's very essential for us to understand that the surface, an area is defined by a single vector. Okay. So, for example, if we ask the question, how many areas does a sphere have? Sfera, sa superfagica. The sphere, it has only one surface area, is a gelacour, because this has a single unit vector which is defining. So we know in spherical coordinate system that we have an r, theta, and phi, right? And AR is the vector which is pointing outward. If you have a football, top footballing, superfagia provisoidal area. Okay? So we come here again. What is defining this surface area? It's actually a vector which points like this. And what is numerical value for the surface area here? A surface area is this. What is this? If you make this into a cylinder, this length is 2 pi r, 2 pi r është kjo. Ka ku dit? Është 2 pi r është kjo. Kemi dhe lartësinë e kësaj që po i quajmë b. Pra këtu, këtë verën e s-s, po ta shumëzojmë me sipërfaqe, çfarë do dalë? Kjo do dalë i në katror, pjesëtim për 2 sigma pi në katror r në kub. So this we multiply with the outer surface area here, and let's assume that the length here is L. We haven't used yet L yet. L is just the length of this wire, and we do here 2 pi r, okay, times L. So now this was watt per meter square, times meter square. So we should get 1. In the meanwhile, we cancel the 2's, we cancel one of the pi's, and the result is going to be equal to I squared times L divided by sigma pi r squared. Because one r cancels out, and in fact, we know that the resistance, it is also defined like the length divided by the sigma divided by area. So this is the resistance of this wire. Okay. So if we look at this term here, this looks to be equal to I squared r. And if you remember from physics 2, you may remember that the energy loss or the energy dissipated in a resistor or in a system, it is equal to, because we know that the power loss, or let's call it power, is equal to VI, right? Probably remember this VI better. And VI is V itself is IR. IR times I is I squared I. Okay, so the power loss. So we can really obtain, what we can obtain from here is that we can understand that the energy loss in a wire, it can be expressed both as I squared R, which is the ohmic loss. So maybe we can write it somewhere. I think we can write it here, which looks like ohmic loss. So in the same way, we can also represent it as a function or as a dependence on the pointing vector. Okay. So probably the numerical, the exact matching between the ohmic loss and the analysis based on the pointing vector, getting the same numbers, this can help us better into understanding of what we have. So let's see for a moment. Okay. Okay, so now when we analyze the so let's assume that we have here, well, so we have average power density. Average power density and instantaneous power density. Now we know that the electric field, we write the electric field in a system like ZT. We can write both the phasor and the phasor and the instantaneous one. But let's keep this one initially. Let's assume that this is AX E0 E minus alpha Z times cosine omega t minus beta z. So this is the instantaneous expression for E. The H would be the instantaneous expression for H would be equal to AY times the magnitude of the electric field. Let's not forget, this is the initial magnitude, but this will be modified, the magnitude will be modified with an exponentially decreasing term along a medium which has some non-zero conductivity. And this one, it will be divided by the amplitude of the impedance, which is a complex number. And this then will continue like this. This is cosine of omega t minus beta z minus the phi, where the phi angle is the phase angle between the E and the H. We know that this phi, for different levels of conductivity, it can be anything between 0 or to 90, or sorry, to 45. To 45, because I think we covered an example in the previous session where the angle, it was something like 15 degrees, but we know that when it is a perfect conductor, this phi, it can get up to 45 degrees. So now, this is the E and the H, but we know that both of these, they have also the phasor notation, not the instantaneous expression. The phasor notation, which is not a function of time, this would rather be like AX E0 e to the power minus gamma z. Okay, so this everything it starts like this. Then this that is minus gamma z, we know that this is equal to AX E0 e to the power minus alpha plus j beta z. Okay, so the gamma is a propagation constant which involves both alpha and beta. So let's not forget this, right? The exact propagation constant, this is alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. So let's not forget this term. And then this will then be equal to AX times the amplitude E0, which will be modified with the attenuation constant. Attenuation means dobsolet signature, e to the power minus j beta z. Okay, so this is the phasor. How do we get the instantaneous expression? From the phasor expression, we do the following. We say that EZT, this is equal to the real part of the phasor, which in this case it is EX, AX, E0, e to the power minus alpha z, e to the power. So we multiply this term with the time propagator. Since now we added the time, m ft e omega t. So we always add this term, e to the power j omega t. This is the time propagator. We add this here, and this is going to be e to the power j omega t minus beta z, and this is still the real part. And the real part of this term is going to be the cosine. So we get ax times e0 times exponentially decreasing attenuation term times cosine of this term. So we get this, right? So as a small reminder, this is how we derive or we find the relationship between the phasor of electric field and the instantaneous expression. So let's take this out. So we have the E and the H that's shown here. Then we can define the SZT, which is equal to EZT cross product with HZT. So we take the cross product of both instantaneous expressions, and this is going to be equal to, we get here AZ will be the direction because AX cross AY, this is what we get here. The magnitudes will be E squared, E to the power minus 2 alpha Z. So we get here E squared, E0 squared, E to the power minus 2 alpha Z, divided by eta C, okay? And then we have here cosine, we multiply the cosine. So this is cosine omega t minus beta z times cosine, we have this other cosine here, omega t minus beta z minus 5. Okay, so this is the expression. We have also a relationship which is something like this, which states that cosine, how can you write this one? Alpha times cosine beta. So this product is equal to 1 over 2 cosine alpha minus beta plus cosine alpha plus beta. Okay, so there is a property of cosines which we write it like this, and with this property, this means that this whole term here, it can be written, or we can say it like this. So we're going to have a term 1 over 2, and here we have cosine alpha minus beta, which is going to be this alpha minus this beta. So we get here cosine phi, okay, because we have omega minus omega t, and this cancel each other, plus cosine of addition of these two terms. Okay, so if we add these two terms, we get 2 omega t minus 2 beta z minus 5. So what we observe here, we observe that so this whole term, this will multiply this factor. So this is a constant term, it will multiply this. What do we obtain from here? It looks like if we have two time oscillatory waves, like this is a time harmonic, this is time harmonic, but it is modified with an exponential decreasing term. If we multiply these two, the energy density or the power density, the instantaneous power density, because this is ZT, nuk e kemi marrë me satarën e kësaj, kjo është në çdo moment. Ju po ne dim diçka që ku kemi një funksion sinusoidal, që është time harmonic, dhe kur marrim mesatarin për gjatë kohës, si e gjejmë atë? This is just a reminder. So we do something like this. We have a sine theta, d theta from 0 to t. What do we mean with this? If we have a sine wave which has a complete cycle like this, I think we take squared here. This is we get the root mean square. So if we square this, the square of this is going to look like, right? So we take the square. Now we are going to integrate over the red line. Okay, the blue line is the real sign. The square is the square of this. So it's going to be negative but positive. We integrate over a full period. Okay, this is the average. But the average is over a complete period. Pra, brenda një periode të plotë që plotësohet vala sinusoidale, ne integrojmë katronin e saj, dhe çfarë do na dalë? Ne mund shikojmë pra thjesht ato është shkruar për të pasur parasysh se si operojnë, por nga ana tjetër ne vëmë re se kjo instantaneous expression of the power density is equal to a constant times a constant term, which does not depend, it's not a function of time, plus an oscillating term which oscillates twice as fast as the electric field intensity. So if this was the electric field which oscillates here to the blue line, we're going to get, let me do it like this. We are going to get the oscillation of the power density. It will oscillate twice as fast as the electric field, which is the source, okay? So this is what you get for the power density, but what is more essential is not power density, but is time average, okay? So that's what I want to say so far. So instantaneous, we wrote this one, it's right here. The average, we denote this one as the S average as a function of Z now. We say this one as a function of Z because when we find the average, we are going to integrate over time. So we are going to lose the time. We won't have time anymore. So this is equal to 1 over the period from 0 to t. As ZT dt. This is equal to AZ E0 squared over 2 eta times e to the power minus 2 alpha z cosine phi. So this is like the S average or S time average, which is going to appear in a system. Now, if the system is not conductive, we may end up having only this. Okay, so for example, the power density, which comes from the sun. Imagine we get solar energy continuously. It's a source of energy for our planet, and and this wave is coming through vacuum. The vacuum, we think it as a lossless medium. So we don't have this term, or you multiply this term with 1. What we are left with is the average power density, which is this term here. Okay, so we can calculate the electric field of the solar line. We multiply, we divide by the impedance, and we get what is the, and also this cosine 0 will also be 1. Why? Because this will have no phase difference. Pra kur ambienti është jo përcjellës, kjo diferenca e fazës midis fushës elektrike dhe magnetike bëhet 0. Kur bëhet 0, përcjellës e 0 bëhet 1. Dhe kur nuk ka fare konduktivitet, edhe kjo bëhet 1. Dhe çfarë bëhet? Kjo thjesht po e shkruaj për një moment, është E0 në katror pjesëtim për 2 që shumëzon madhësinë e intrinsic impedance. So in this case, this is, let's call this air or vacuum. So if you want to see how much energy is the sun carrying to our planet, we use this expression. But if it is a rainy day, if it is a humid day, because once you have humidity and when it is raining, the air vacuum is conducting or is non-zero. That's why we see the thunder, right? You see the thunder, so it's conducting. You see flashes of light, which means that now these terms have to be included. But if the conductivity is small, probably this cosine phi is not 1, but who knows? It's going to be 0.99, 0.89, 0.95, something close to 1, but not to 1. And also, this is going to be slowly attenuated. So there is a huge volume where there are clouds or where there is rain, and as the sunlight is coming, it will be attenuated. If it's cloudy, you might not even see the sun. But let's assume that we're just analyzing the propagation of the electromagnetic field wave as it is passing through the clouds. Initially, it will be attenuated by these factors depending on what this alpha is going to be. So it's just because the difference between a sunny day and a rainy day, or a day which is cloudy with humidity, like in the summer, if you stay close to the sea behaves like a boiling pot. So you sit next to, in the kitchen, you are cooking something and the water is boiling, so you have a lot of humid or a lot of air and water molecules flowing around. the same thing happens in a city by the sea during the summer. So the whole sea is providing so much water, and humidity is different from zero, that probably you get this term or this expression when compared to this expression for dry air. Okay, so this is something regarding the Poynting vector. Do you have any question? Any question regarding anything? Okay, if you have no question, we can stop for today.